Topic is about escape the maze. Problem overview. What does it mean to escape the maze? The maze escape problem involves finding a valid path from a starting point to exit in a grid-based or graph-based environment with obstacles. It is a classic example of a such problem in computer science, often used to teach fundamental algorithmic thinking and state space exploration. Mazes can be represented as 2D grids where cells are either open, transversable, or blocked walls, with movement allowed in 4 or 8 directions. The goal is not just to find any path, but often the shortest or most efficient one depending on the algorithm and constraints. This problem has real world analogs in robotics navigation, GPS routing, and game AI pathfinding. Modeling the maze graph representation. A maze can be a maze can be modeled as a graph where each cell is a node and edges connect adjacent transversal cells. Each node stores its coordinates and whether it is accessible, while edges represent possible moves between neighboring cells. This abstraction allows us to apply general graph transversal algorithms like BFS and DFS to solve the maze. The graph may be implicit, generated on the fly during transversal, rather than pre-built, saving memory for large mazes. Directional constraints, example only up, down, left or right, define the edge connectivity and affect algorithm performance. Next, BFS, breadth first search, level by level exploration. BFS explores the maze layer by layer, visiting all nodes at distance d from moving to distance d plus 1 from the start. It uses a quick to manage the front layer of nodes to visit, ensuring FIFO order and systematic expansion. BFS guarantees finding the shortest path in an unweighted grid, making it ideal for optimal maze exchange escape. Level by level exploration. It uses BFS guarantees finding the shortest path in an unweighted grid, making it ideal for optimal maze escape. Time complexity is O V plus E, where V is the number of cells and E is the number of adjacent connections. Space complexity is OV in the first case due to Q storing all nodes at the current depth level. DFS, depth first search, going deep before wide. DFS explores as far as possible along each branch before backtracking, using a stack or recursion to manage the search handler. It may find a path faster than DFS in some mazes, but does not guarantee the shortest path, of course. DFS is memory efficient with OV space in the worst case, but could get stuck in long detours in complex mazes. It is useful when any valid path is suspicious, such as in maze generation or when memory is limited. Cycle. Cycle detection is essential to avoid infinite loops, typically done by marking visited nodes. A star search, heuristic guided optimal pathfinding. A star combines the strengths of BFS and greedy best first search by using a cost function Fn is equal to Gn plus Hn. Here G bracket n is the actual cost from start to node n and Hn is a heuristic estimate form from n to the goal. Common heuristics include Manhattan distance for 4 directional movement or Euclidean distance for 8 directional. A. A star is optimal and complete if the heuristic is admissible, never overestimating the true cost to the board. It expands fewer nodes than BFS when the heuristic is well chosen, making it faster in practice for large bases. Heuristic functions choosing the right guidance. The Manhattan distance heuristic counts horizontal and vertical steps needed. Ignoring diagonal sign is ideal for grid mazes with four directional movements. Euclidean distance uses straight line geometry and works well when diagonal moves are allowed. A heuristic is admissible if it never overestimates the actual distance, ensuring A finds the optimal path. Consistent or monotonic heuristics satisfy h bracket of n less than or is equal to cost n comma n bar plus h bracket n bar for all neighbors, enabling efficient updates. Poor heuristics may degrade A star to behave like BFS, while strong ones dramatically reduce the search space. Comparing BFS, DFS, and A star traits in performance. BFS guarantees the shortest path but may explore many unnecessary nodes in large open areas. DFS uses less memory and may find a path quickly but risk long, suboptimal routes or infinite loops without cycle checks. A star typically explores the fewest nodes among the three when using a good heuristic balancing speed and optimality. In worst case scenarios, all three algorithms have OV space complexity, but A star often has better average case time performance. Choice of algorithm depends on maze size, required path quality, memory constraints, and movement rules. Implementation considerations, data structures, and efficiency. Use a queue for BFS, a stack or recursion for DFS, and a priority queue min heap for a star to manage node exploration order. Maintain a visited set or Boolean matrix to avoid revisiting nodes and prevent infinite loops. Store parent pointers or a path reconstruction map to trace the final route from goal back to start. For large maze, consider memory efficient representations like bitmaps or compressed square structures. Pre-processing the maze layout can improve performance such as identifying dead ends early. Handling complex maze features. Loops and multiple exits. Mazes with loop require single detention to prevent algorithms from revisiting the same cell identifier. When multiple exits exist, the goal becomes finding the nearest one, which BFS and A star handle naturally. Algorithms can be modified to stop at the first goal reach BFS or continue to verify optimality A star. Dynamic obstacles or moving walls require real-time replanning, extending the basic static maze model. Weighted mazes, where some paths cost more to traverse, necessary directions or A-star instead BFS paths. Practical example, solving a 10 into 10 grid maze. Consider a 10 into which started no goal at 9 started was as blocking direct. BFS would explore out 14 consecutive layers, guaranteeing the shortest path in terms of steps. DFS might take a winding route, possibly reaching the goal faster by line, but with more steps. With Manhattan distance would focus exploring toward the goal, expanding fewer nodes than BFS. Visualizing the such process shows how each algorithm prioritizes different regions of the maze. Extension and real-world applications. Maze-solving algorithms are fundamental in robotics for autonomous navigation in unknown or structured environments. Video games use variants of A star from NPC pathfinding, often with navigation messages instead of glitches for efficiency. Thank you.